All right, so here we are. We're going to design our L-beam. Let's put this on slide mode. Let's see, there we go. So here we are. We are designing this L-beam in this fashion. So both ends of this aluminum beam will be fixed, and there's going to be a hole right through here where will put a bolt, and that bolt is going to be for holding about 1,000 pounds weight, and the dimension of this beam is 4 feet in length, and it's a 2 by 2 with a thickness of a quarter of an inch. It is an aluminum 6061 T6 with a yield strength of about 40,000 psi. So that's basically what we have, and we want to see whether this L beam, the way it is with the properties and its characteristic, are enough. This here is sort of like a washer. Okay, so the ball goes right through here, right through the hole, and let's look into that. So this is another view of what we are saying. Here is kind of an eyeball that is going to be connected right through here. The diameter is about 3/8 of an inch, and the washer is about 1 inch. So we have 3/8 right here, the diameter, and 1 inch right here, holding this 1,000 pounds. So that's basically the idea. And again, check this out, right? Because it's the gravity go this way, so that when we do our analysis, we don't get lost. All right. So basically, the idea is to do the analysis on Solidworks and see how the stress will looks like, when we submit our uh, L beam to that force. So you can see we got a maximum value of about 32,000 psi versus the allow of 40,000. That's one point. The second is the amount of deformation was about 0.153 inches of an inch, which to me is almost like nothing. As you can see right here, the deformation that you see here is just for illustration. It looks huge, but it's not. And you can see that both ends are fixed. So the force will go right through here and through the eye bolt uh, that is going to be holding the 1,000 pound. So deflection. Talking about deflection, depending on what code you look at, like for example, this is kind of interesting. The International Building Code is called for L over 360 for deflection. I mean, obviously there's some important condition where we want to be sure that there's pretty little deflection or nothing at all, like supporting plaster. Then that has to be L over 360. We do the math with the 4 feet that we have, multiply that 4 by 12 divided by 360. That's about 0.13 of an inch. So in other words, 0.13, meaning that this is slightly above that limit. So you might have to make this thicker if that's were the case. But this is not for a ceiling. This is this is for another application, like a holding an engine, which weigh about less than 1,000 pounds. All right. So if you fire any software, the maximum bending moment will be right at this point here, which is talking about 500 pound per foot. So here, 500 pound per foot. Now, if you do the analysis for your stress, that would be about 24,000 psi. Based on the fact, remember, the centroid is 0.592 and the maximum, so that would be somewhere here. So the maximum distance is up to here. So this part will be subjected to very high stress that will come out to 24,000, which is kind of close to the 32,000 that we got for SolidWorks analysis. Remember, the gravity is going this direction. So you think about it, at the end of this line here, there's going to be a lot of tension. And so tension here, and here in this part will be compression. So you have tension, more tension, and finally compression right through along this line. All right, so let's see. Anything else that I should say? Well, actually, nope. We are in pretty good shape. What we should do now is let's take a look how we do this type of analysis within SolidWorks. Let's do that. Oh, well, here we are in SolidWorks. Let's see if I can construct my L-beam. Let's see, what would be a good start for this? Maybe a right. Yeah, that might do. Right plane. So let's start with that. And let's see. Let's put a line. Let's see how this will work. All right, let's say that that line will be about that would be 2 inches, and we do another one from the center up. All right, I think that's 2 inches as well. Let me double check. That looks good. Yep, 2 inches. Now, oops, what happened here? Now, let's throw another line here, and good, and let's leave it somewhere here, and that line should be, let's see if I can do something here. That line, the length of that line should be, since we want a distance from the bottom of 0.25, that line should be 1.75 in length. And so let's move the line. Let's see if I can move it, because somehow it's fixed here. Oh, it's giving me some trouble. Let's delete the line again. Let's see if I can move it. There, but somehow, let me see if I can get this right. That's the problem. That one should be 0.25. And now let's see if I can move this up. Oops. There we go. Now we're talking. So close. Let's close the guy. Let's see if I finish it. Now the only thing that I need before doing that, actually, let me be sure that this is where it's supposed to be. That should be 0.25, and it looks good. Now another line. Up to there, and now another line up to here, and I think it's getting almost done. Another line from here to here. Excellent. Now it's close. So we got all the dimension. It's about 1/4 inch thickness, and everything looks good. So we accept that. And how about if we go feature, extrude, and can go any either way. Actually, let's keep, I don't know, mid plane, and that would be 2. That would be so it's going to be 4 feet, meaning that we should go, like, for example, it would be 24 inches. Now Let's get this side to fit so I know what I'm doing. It look good. So we accept that and we rotate again. Let's see how this looks like. Yeah, we got our beam pretty much designed the way we want it. Well, the issue is that the force here will be in this direction here in one of the beams. So this beam will be fixed and this is going to have a force going in that direction. It doesn't matter what is up and down just to be, but what I'm saying is that you have to be sure that depending either side, because they are equal. So like for example, this size would be, this length here is longer, then you have to be careful where is the hole according to your original drawing. In this case, it will not matter. So I can put it here or here where the bolt, the eye bolt will be, hook up for the weight, for the force that will suffer when we do the analysis. Now, let's see. And this is the part that is important. Before I do anything, let me do, let's go top plane. Let's see, front plane. I think the front plane will do. Let's see, rotate. Yeah, front plane will do. And let's work on the front plane. And let's do sketch on the front plane. And let's add some line here, just so I know what I'm doing. Good. Now, let's see. Actually, this will look better if I get this right where it's supposed to be. Let's see if I can fix this. Good. How about this one? There we go. Now I have the middle, and that will do. Because then the next part will be right here. We're going to add a circle right in the middle. That will do. And so that one, actually, let's make this bigger so I know what I'm doing. Let's see if I can, oops, escape. Zoom, let's zoom this out. That should be a 3/8 of an inch for a hole, 0.375. Let's accept that. And let's do, oops, yeah, we deal with that later. Let's do now the washer. So let's do 2 more circles. Let's do a big one, which is about an inch. And let's do another one that is slightly larger than the hole. That will do. All right, so let's fix this one, definitely. And let's put that in 1 inch. And that's it. So we got the inner hole and the washer outside. And there's not a washer yet, but eventually is where the force will be concentrated. And that's very important. So let's do here, what I have to do now, accept this, and let's go through, let's do quickly here. Let's see. Let's go features for 1 second. And let's see one thing. All right, let's do a through cut. Let's see how this looks like. And now let's rotate this so I know what I'm doing. Okay, more or less. All right, so I can certainly do mid plane, and it will cut through, no problem. Accept it, no big deal. So let's see, rotate. There we go. See, that's for the bolt, and the other part is for the washer. And that's the important aspect of this. So we gotta be sure, we wanna be sure that this is spotted right versus the total area, because the force now will be concentrated around the washer, okay? And this hole will be sort of like a weak spot because you make a cutoff out of the uh, beam, or inside the beam. So let's do that. Let's zoom out again a little bit. Let's see, and let's do here what we have to do. See if I can go back again to my sketch there. And what I have to do here is, let's see if I can pick first of all. Sketch. Let's see if I can do larger. I'm using a regular mouse, so life is hard when you have a regular mouse. So let me see if I can do now the identification is right there. Now let's see if I can do split line. It looks that is projecting right. I mean, this is one color and these two have the other color. Now the face, it seems right as well. I would say that looks good. At this point, it looks good. So using the split line, the part of the silhouette is getting the silhouette right. So, and the only thing, and the face as well. So the only thing that I need to do is just accept that, and I think that we are pretty much ready to do the analysis of this. Let me redo this part here, and let me mess around with this a little bit. Let's rotate. Yeah, you can see the silhouette of the spot for the washer, and so everything looks good. With that said, I think that what we need to do now is basically do the simulation part. Let me get out of here, and let's see, we go to, and then we do, I think that we are pretty much done. I'm waiting here. There we go. Simulation. How about new? Actually, one thing that I haven't done is select the material. I will select it now. Don't worry about it. So let's say it's static. It's okay. And how about if I edit the material, and what is going to be? It's going to be aluminum alloy. And which of the alloy are going to be using? Let's see. $6061 T6 sounds good to me. Let's see, it's about 40, the yield strength, about 40,000 psi, the unit that I like. English, and that will do. Let's apply that, close, and now let's start with the features. Let's see how we're gonna do this. Fix geometry. We're gonna fix this part. Now let's rotate this because we're gonna fix this part as well. So now I got both parts fixed. So the question is, let's see if I can rotate this more. So it is through the wash. Actually, I have to see it. It's just that for deformation, it's nice to have the piece, the piece of your working in such a way that you can actually see how things will behave. But I would say up to there is okay. Let's leave it there. Now, so end of the story. Fix at both ends. Whoops. No. What you doing? Get that out. There we go. Now, it is phase 1 and phase 2 according to this. So we are in good shape. Now, let's accept that. And now let's see external load. And this is the part that is important of what I did with the split line. External load, let's do a force. And the force will be English. And here's the 1,000 pound. The question is where the 1,000 pound will be located. The whole surface? No. It's going to be, no, it's right there. See? So that's the beauty of this. It's a concentrated force right at the washer. If the direction is not right, you can definitely change the direction. And that would be through the bottom of how you fix the surface. So that's how we're going to install the beam. So the force is toward this direction. All right. So with that said, I think that we are pretty much done on this. It is fixed. We have the spot. The next part is the mesh. Let's go to the mesh for 1 second here. And let's do create mesh. I like always to do sort of moving on to the fine line a little bit, so that doesn't take too much time. Now, in terms of mesh parameters, blended, always good. How about this one? Everything else, I'll leave it the way it is. Accept that. We are done. And now, so I think that we are ready to run this study and see. It looks good. I like it because you can see that there's a lot of definition within the 0.25 inches of the thickness for the L bar. Now, run this study. Let's see how this looks like. There we go. Well, it's interesting that I like it is the scale deformation is about 16, meaning that this is well exaggerated. But I don't like the unit, kind of confusing to me. So let's change the unit here for a second. Let's edit chart options. Let's start to mess around with this one a little bit. So show max annotation. I like to see that number. And what else I need to look at? I like to go with better with the yield strength and normal, scientific. Let's use general. Now I have to change something else here. Let's see settings. Definition. Oh, here we go. I don't like that. PSI, that would do. And so right now it's about, 40 KSI. And still looking into chart option. Let's see. Scientific, no. General. Let's see if that would do. I still like it. I guess I'm putting too much decimal places. Let's see how this looks like now. Animate. So let's see. That was too fast. I cannot. Let's see. There we go. There's one spot actually within the hole for the bolt that is causing a little bit getting close to the red. There's a red spot right there in the maximum actually. Let's get out of here for 1 second. and you get that value of 3.17. That means about 31 KSI, which is still below the yield strength of 40, basically KSI. So it's okay. Now, how about the displacement? Let's see, displacement. Displacement, um, hmm, in millimeters is about, let's see, can I change the unit displacement? Edit definition. Of an inch. Yeah, point 0.1, 0.15 of an inch, which is perfect. It's pretty much what I calculate from the other system. Let's see, through the other hand calculation show that deflection will be about, did I got the number? I think it was 0.15. If I record that, between 0.14 and 0.15 of an inch, which is perfect. Actually, the hand calculation for deflection show a value of 0.1656 inches, slightly above from the value of the Solidworks simulation. And but everything else looks super. Very little deflection, although well exaggerated here, just for animation purposes, but it looks good. Actually, let me do one more thing here. Chart options. Let's see what I got. There we go. Looks much better now. And let's see. I'm looking for, actually here, let's see. Chart options. Okay. Look good. Nothing to change there. See definition. Okay, settings. This is what I like. Superimpose the original model so we know how that looks like. And let's see if I can. Let's see. Yes, the original model is right there. It's sort of looks like a shadow. Let's see. Animate, and you can see getting against the shadow how the deflection looks like. And let's see what else I can do. Let's see. Okay, let's stop this for 1 second and let's see if I can rotate the view so that it could get better. There we go. That's actually better. Just to see the effect of that force over that surface. The exaggeration, I mean, really killed me. It's like, wow. You get scared when you see so much deflection, but it's not. Just part of the illustration, how things are being deformed. That's about 1,000 pounds. That's a lot of, I mean, that's almost like that's a very heavy, I don't know, thinking about an engine or something like that, 600, 700 pound engine, meaning it's a truck engine or something like that, cannot be a car engine. But let's see, I think that will do. Let's do the deflection study there and see how this looks like. Stress again, animate. So this is what's happening. See this part here as well, bending, but it stay on the blue. So very, very, very little. Actually, sorry, this is the stress on the unit. Very little. It's just stay to about about 8,000. That's 8,000. Not very well below. Only the red spot is seen very little here, which is what's getting close, but it's not that a big deal. Still okay. Let's see. Let's rotate again. This I don't like that one. This one, sorry. There we go. So the maximum is about 31,000, but the yield strength is 39, 40. I would say 40. So it's perfect. No, nothing else to consider except if you find that this deflection is way too much for you, then you can either increase the thickness of your L-beam here, which is about 1/4 of an inch, or change the material you're using. In this case, is aluminum, and is 6061 at T6. And basically, that will do. The next video that I'm planning to show is what will happen if, let's get back to, let's see, to the original, my original design. Let's see, let's go back to, there we go. Just for, what will happen if instead of force going like this, in this way, the force, you make a hole here and the force go that way. So the force is within the bolt, with one of the face of the bolt, and that's a different story. So I have to do a split line, but within the inside of the hole here. What? This is kind of confusing. Let me start again. This is what I'm saying. Let's say that you have your L-beam the way it is shown here, but then you make a hole through the L-beam, and that hole will be in shear. So you put a pinball like shown here, and the 1,000 pound will be pulled down. However, that will be at the face of the bolt here, meaning that I have to do a split line to ensure that I get this right. So this pull down on the L-beam. So that's basically it. With that said, thank you a lot. I really appreciate you watching this and watching me goofing through all this. But it's a learning experience. Have a great day. Bye.